Hello dear students, in the previous lesson we solved example 1. Now we discuss about the cylindrical capacitors. An example for the cylindrical capacitor. In this I solve example 2 about the cylindrical capacitors. Example 2. Before going to example 2, let me introduce the what is cylindrical capacitor is. So cylindrical capacitor is basically it has two plates in the form of a cylinder. One is the inner cylinder. Inner cylinder has radii RA or R1, and the outer we have outer cylinder that has radii RB or R2. So in the cylindrical capacitors we have two plates that are separated by distance d. There is a separation between the two plates. The plates are in the form of a cylinder. So in this case one positive charge is spread on the inner cylinder and negative charge is stored on the outer cylinder. Negative charge is stored on the outer cylinder. Okay, one more thing. So the outer cylinder has radii R2, inner cylinder has radii R1. So there is a separation between the gap between the two cylinders. So they act as a capacitor. So if we connect one plate to the positive terminal, so if basically we connect inner plate with the positive terminal and we connect outer plate with the negative terminal, so that the outer plate will gather or will spread the negative charge and the positive charge is stored on the inner plate, so that the positive charge stored on inner and negative charge stored on outer cylinder. Inner has radius R1, outer has radius R2. So now we solve example number 2. Okay, we have a cylinder and we need to determine the formula for capacitance for the cylindrical capacitors. Okay, so in order to derive the formula for cylindrical capacitors, we use previous formula for intensity E, because we know that there are two or three steps to solve for this. In simple, we first find electric field intensity E. In the first step we just give the charge on the capacitors, then we solve for intensity E, and then we solve for V, and then we solve for C. So there are three simple steps. So first we find for electric field intensity E. So as we know that from the previous is that electric field intensity for cylinder is E is equal to 1 over 2 pi epsilon naught lambda over r. So lambda can be written as charge per unit length over into r. So this is formula for intensity of cylinder. Okay, now we use this result in order to find the capacitance, and VBA is equal to, our potential difference between BA plate is equal to minus E dot dl. So we put this intensity formula in this equation, that 1 over 2 pi epsilon naught Q over LR into dl and into dl. So dl can also be written as dr, because the distance is radii here between the plates, the distance is dr, so we can write as dr. So VBA. Okay, now we take constant terms to the outside of the integration. So I solve here. VBA equal to, so constant terms are minus 1 over Q is also constant, charge is constant, 2 pi epsilon naught, L is also constant. So the radius RA to RB. So in this example we know that there are two radii. Inner cylinder has radii RA, outer cylinder has radii, inner cylinder has radii RB, outer has radii RA. So we need to integrate from RA to RB, because the length element, the separation between the plates is D. So this D is length is separation between the cylinders is basically D. So we need to integrate from A to B, RA to RB. okay, RA to RB. Now so that the only that variable term is R in this case, so 1 over R into dr. So this is equation number 3. Now we first integrate, we solve integration separately. So 1 over R integration of 1 over R is log of R, simply log of R. So we can write equation 3 as VBA is equal to minus Q over 2 pi epsilon naught L, and now log of R is the integration, and now lower limit RA, upper limit RB. So we put our limits minus Q over 2 pi epsilon naught L, 2 pi epsilon naught L, log of RB minus log of RA. So we know that the log RB minus RA, so this negative sign can be removed with the negative sign is equal to 2 pi epsilon naught L or log of RB over RA. So the negative sign can be removed with the division, because this is a log rule that negative convert into divisions. So this is potential VBA. But we need capacitance. So capacitance can be found by using the formula C is equal to Q over V. C is equal to Q over V. Now we go here. So solve from here. C is equal to Q over V. So there's a potential is minus Q over 2 pi epsilon naught into L log of RB over RA. Now we can remove the negative sign by reversing this logarithm, but we can also remove this negative sign. But if I remove this negative sign from here, it is better. So negative will become positive. So this term can be rearranged. So we can write RB and RA like this. It's a better way to remove the negative sign here. So log of, instead of write RA minus RB, we can write log of RA minus log RB, and this remove the negative sign. So we have Q over 2 pi epsilon naught L, log of RA over RB. So log of RA over RB. Now this Q will be removed, so this term can be taken to the numerator 2 pi epsilon naught L. So we are left with the 2 pi epsilon naught L over log of RA over RB. So this is the formula for capacitance C. Okay, now there is a special case. Note, if RA and RB is very small, what does it mean? It means that the space between the plates is very small. RA and RB, the space between the plates is very small. Mean, if in this case, let me explain this. For example, if we say that this is RA, inner radii, and outer radii is the very small distance between inner and outer radii. So the outer radii is also near to this one. So we can say that very small gap between RA and RB. So RA is approximately equal to RB. So you can say that RA minus RB is equal to delta R, very small. Delta R is very small. So in this situation, we can put RA is equal to del R plus RB in the formula of capacitance C. So C is equal to 2 pi epsilon naught L over log of RA over RB. So we put R, instead of RA we put del R plus RB over RB. So we replace RA with the del R plus RB. So we can further solve, so we can also separately solve this term. So further, this is equation number 2. This is equation number 4, equation number 4. Okay, now we can solve this one. Log of R del R plus RB over RB, which is equal to log of del R. So we can write del R plus del R over RB plus 1. So we then